Okay, so we'll talk more about high frequency propagation on how we get the long distances somewhat reliably. It's still dependent on sunspot activity, but most HF signals can be bounced off of the ionosphere. So you can get contacts literally all around the world. I play with FT8 a lot, which is one of the digital modes, which was kind of developed out of some stuff that Joe Taylor did for deep space communications to talk to satellites and stuff that were like out of the Earth's or our solar system, I should say. And they're able to pick up signals that are 20, 25 dB below the noise level. So a lot of times it's very easy to make contact with stations in Australia and New Zealand with just a simple vertical antenna. The ionosphere is actually created because of solar radiation that's being generated by the sun. And sunspots are really kind of like holes on the surface, so it allows a lot of that radiation to escape, which is why the higher the sunspot activity, the more ionization that we see on the ionosphere. And that ionization, like we talked about last week or week before when we talked about free electrons, causes those electrons in the oxygen and nitrogen and other gases that are out there to get enough energy that they actually escape the atom and become free electrons. So you have a charged field up there, and that's what's reflecting the radio waves. So in like 50 to 600 miles is what we call that ionosphere. Troposphere is way down below that. And I don't know why they labeled them D, E, and F. You would think that somewhere there's A, B, and C. I've never seen A, B, and C referenced. Maybe that's the troposphere. I don't know.
Could be.
But the D layer is the lowest layer that gets ionized. And the F layer is the highest. The one on the right is showing the difference between night and day, where at nighttime you basically are down to 2 layers. And the E layer is actually kind of thin. The daytime, you got all 4. This other chart is kind of showing the height of these different troposphere, stratosphere, mesosphere. So the ionosphere is in the thermosphere. But you don't need to remember that. Here's a prettier chart showing signals in the medium frequency up to VHF and how they interact. So you can see some of them are actually being refracted in the E layer. And then some of them actually make it up to the F1 and F2 layer. If the frequency is too high or the angle is too high, then they just go straight through. But that also allows you to have communications with things in space. And you're usually doing that in the VHF and UHF bands. There's just another kind of the same thing, showing different frequencies over here on the left and what the ranges might be. A similar thing over on the right at nighttime.
Yeah.
And one more, showing the difference between a 1 megahertz signal and a 20 megahertz signal and how it's refracted. So the 20 megahertz is going to go a lot farther.
But there could be interference, or I'm sorry, because it showed us like a dotted line. Is that like some of the signal is absorbed? Would it weaken the signal?
I think it's just trying to show that it's being refracted.
Okay.
In actuality, part of the signal is probably still going straight through.
Mm-hmm.
There's a thing when we get to the extra class license where they talk about ordinary and extraordinary waves and how they split.
Mm-hmm.
But we don't want to talk about that now.
No, not yet. Oh, wait.
And this another one showing UHF and going straight, VHF, maybe some bending, the lower VHF being refracted, possibly. So which region of the atmosphere can refract or bend HF and VHF radio waves?
Charlie.
What is a characteristic of HF communication compared with communications on VHF and higher frequencies?
Long distance. I would say Charlie.
Okay. Okay, sunspot cycles, we talked about those.
Mm-hmm.
The 6 and 10 meter bands are much more active when there's many sunspots. I mentioned that it's a 11-year cycle.
Mm-hmm.
So I guess actually we're farther into the cycle than I thought. So cycle 25 started in 2021. I thought it was later than that. But the more more sunspots, the more radiation, the more ionization, the more refraction. I think I had that chart earlier, so nothing different about it. It does show an the invis we talked about. And this one too, where, in the daytime, we're getting refraction off of the F1 and F2 layers. And at night, everything kind of collapses and lower frequencies work much better. Which of the following bands may provide long-distance communications?
All I keep seeing is alpha.
Well, okay. Because 23 and 70 centimeters and 1.25 meters don't do it.
No, centimeters just wasn't cutting it for me.
Okay. That's a short wavelength.
Very short.
So the ionosphere isn't exactly stable. The sun's rotating. It's always creating and losing sunspots. So the amount of radiation that's hitting the ionosphere is varying during the day. And the atmosphere itself up there isn't exactly constant. So you could have cases where in those other diagrams, they show the layers as nice round uh, bands with a smooth edge. In reality, it's not necessarily a smooth edge. So refraction off of the rough edges of those layers may behave differently from minute to minute. So you have to take into account the fact that the ionosphere isn't totally stable. So you can get what's called fading, where you can have a strong signal and then it fades down to where you almost can't hear somebody, and then it comes back. Can also be due to something like a multipath, where you're getting that same signal via two different paths, and it's causing interference, and it can either add or subtract. It's even possible to have a signal come back via what we call the long path. So the short path would be from you to, say, a quarter of the way around the world. The long path would be from you in the opposite direction, 3/4 of the way around. So you get that signal delayed, so you get an echo. And that's not uncommon, depending on how active the ionosphere is and the solar activity. So main thing here is the lower bands, the 160, 80, and 40, work the best at night, not very well in the daytime. The 20, 10, and 15 work very well during the day. 20 happens to work well at night also. I don't see much difference in 20.
Okay.
This is a standard radio band chart showing from the, and this is a fairly new band that they've adopted, the 2200 meters. It's kind of weird. You're only allowed 1 watt. All the way up to the 23 centimeter band. Most amateur radios tend to operate over here in the probably 160 up to 6, and then a VHF UHF radio is going to be possibly 6 up through 23 centimeters. Not sure there's a radio that covers that entire spectrum.
Okay.
So what is generally the best time for long distance 10-meter band propagation via the F region?
That'd be shortly after sunset's dawn. No, dawn. Charlie?
I'll read the whole thing.
Dawn. Long distance.
What's different about the first two and the second two?
Well, one is dawn to sunset, sunset to dawn. Well, it's the high sunspot activity and low sunspot activity that's got me right now.
Okay.
The long distance, oh, that would be yeah, long distances is going to be at night. So,
Oh, 10 meters.
I'll say Bravo. Go ahead, shoot me.
Daytime.
Long distance, 10 meter. Oh, I got the wrong numbers. Okay. Best time for distance, gotcha. Okay.
Daytime. 20, 15, and 10. And the higher the sunspot activity, the better they are.
Gotcha.
What is the likely cause of irregular fading of signals propagated by the ionosphere?
I'd say delta.
Okay. Yeah, we didn't talk about Faraday rotation yet.
That's why I laughed at that one.
What's the real thing?
I know, but we haven't talked about it. That's why I laughed.
Antenna polarization. Okay. And we talked about some of this before.
Mm-hmm.
But when you're refracting off the ionosphere, a strange thing happens. I can't explain why. I've never really looked into the why. But when the ionosphere refracts or bends that signal, it also changes the polarization into what we call elliptically polarized. You could say circular, but circular is a special case of elliptical where the E field is the same strength as it rotates. Elliptical means that instead of being going around in a circle, it goes around in an ellipse where one angle can be greater signal strength than another. And that's an effect of going through the ionosphere and coming back. So it turns out, because of that, for HF, you don't care whether you've got a horizontal or vertically polarized antenna, because the ionosphere is going to convert it to elliptical. So you'll be able to transmit and receive from a horizontal to a vertical or a vertical to horizontal.
Gotcha.
Or even better yet, an antenna that's circularly polarized. So which of the following results from the fact that signals propagated by the ionosphere are elliptically polarized?
Bravo.
Okay, so we learned that the ionosphere refracts HF and lower VHF signals. We can get long distance propagation on HF that we can't do on the higher frequencies. You can have fading due to the random combining of signals taking different paths. Kind of that old multipath thing again. The sunspot cycle affects long distance on 6 and 10 meter bands, probably more than the others. And the 10 meter band is open during the daytime. And as far as polarization, because the ionosphere converts signals to elliptically polarized, we don't really care what our polarization is on the antennas we use. Now, if I'm trying to do VHF, single sideband, I'd want to use a horizontal. Because if somebody's listening for that, is more than likely going to be horizontal.